All right, guys, this is homework 10, question number 3 here. So what we have is a pion, which is just an elementary particle. And we have its lifetime when it's at rest. And then we also have, like when it's moving, we see a new lifetime. So basically we have some difference between a stationary and moving frame. So kind of an easy way I think about it. Well, I mean, you know which equation we're gonna use. We're gonna use we're gonna have some time dilation here. So we're gonna have some delta t is gonna be equal to the delta t naught divided by the square root of 1 minus b over c squared. Okay. And then delta t is like the stationary frame, right? So that means the stationary frame will see the event happening slower because like the time is dilated for them. And then the t naught, that's in reference to the moving frame. They're going to have the normal time, right? So kind of a nice way I like to think about it is delta t naught is always smaller than delta t. So sometimes I get confused. I'm like, wait, which one goes where? And then I look at the magnitudes of them and I see 2.6 times 10 to the minus 8 and 5.5 times 10 to the minus 8. Because I remember that delta t naught is going to be smaller than delta t, I know that I'm going to be plugging in delta t naught is equal to 2.6 times 10 to the minus 8, and then delta t is 5.5 times 10 to the minus 8. That's just a little nice way I remember it. And what we're looking for is some velocity. So basically what we need to do is get v to one side. So it's going to take a little bit of moving things around. So let's first move the, let's get our stationary, and let's get our changes in time, our times on one side, and then get rid of that square root. So it's going to look like a, it's going to be negative, or sorry, delta t naught divided by delta t is going to be equal to, or that's squared. Let's get rid of the square root here. Is going to be equal to 1 minus v over c squared. And then we're going to need to move one to the other side, square root, so to get v over c. So then v, so therefore, v is going to be equal to c square root 1 minus delta t naught divided by delta t squared. Sorry, that's pretty bad handwriting. Like that. And now all you need to do is plug in. And remember, I told you what delta t naught is going to be equal to and what delta t is going to be equal to. You have your velocity and you're going to solve for it in units of, and then you're going to solve for it. It's going to be some decimal and then c, right? Because we have that speed of light there also. Cool. I'll let you guys plug that in. Okay. Continuing with question 4 here. So we have a scientist has a cat that lives 9 years old. Okay, so we brought up a good point. Like that is the normal time. And what experiences the normal time? The moving frame. So when I say delta t naught, that is the normal time. And that's, again, experienced by the moving frame. So maybe I should, just to be very clear, I'm going to write out my variables that are in the question because I know it can, excuse me. Excuse me. I know it can kind of get confusing. Oh, so not 9 years. Okay, so 9 years. When Felix, the cat, is born, it is placed on a spaceship and blasts off at a speed of 0.8 the speed of light. Also, like people often ask, what are relativistic conditions? It's when you're at least 1/10 the speed of light. That's kind of a rule of thumb. So then in part A, or part 1, let me say that. Part 1, how far from Earth, as measured by an observer on Earth, is Felix when it dies? So we're looking for some distance, right? But to be able to calculate that distance, we're going to need to manipulate the question such that we have a certain amount of time, because we know the velocity we're moving, but we don't know the time. And remember that velocity times time is going to be equal to that distance d. So we can set up our equation. Delta t is equal to delta t naught divided by 1 minus v over c squared square root. Okay. And we're told that like the cat has a normal, it's the normal life of the cat is 9 years. So we have the normal time. That means we have delta t naught, plug in 9 years in the numerator, and then we can plug in 1 minus 0.8 c over c squared, get rid of those c's here to cancel out. And then what we're left with is going to be equal to 9 years over the square root of 1 minus 0.8 squared. Oh, let me put the squared on the inside. No one gets confused. Squared, and we should get, I don't know. Let me plug into my calculator one second. Okay, so we got 15 years, and then the next thing we're going to need to do is we're going to calculate distance, right? Because remember, v is going to be equal to d over that amount of time. So what we'll say is d is equal to v delta t. We just solve for that. So we have 0.8 c, we know how fast it's going, times 15. Well, let's plug in what c is equal to. C is equal to 3 times 10 to the 8th meters. We're to get our units in here. Let's just be nice with our units. And then 15 years. And then if you remember from Gen Chem now, we're gonna need to convert these years to seconds here. So let's do 365 days in 1 year. We have 24 hours in 1 day. And then continuing over here, we have 60, wait, did I do hours yet? Yeah. 60 min in 1 hour. And we have 60 seconds in a minute. Okay. And now all those units will cancel out, and we're going to be just left with the meters here, because we'll see that these years cancel out, this day cancels out, these hours cancel out, mins cancel out, and then this second over here and this one over here cancel out, and all we're left with is meters. So now we solve for d in terms of meters, and that's equal to 1.14 times 10 to the times 10 to the 17. Let me just double check. That was an old. Let me pause it quick. All right, so that's 1.14 times 10 to the 17 meters. Okay, so now we know how far away we are when Felix dies. And then we want to know in part B, we want to know that the spaceship sends a signal back when Felix dies. How long after Felix was sent off does the signal reach Earth? Okay, so this is part 2. So we're going to need to find, okay, so we know V. Is there anything about this for one second? Okay, so for part 2 here, sorry, I just wanted to work it out because I was getting a little mixed up in the working. So we have the spaceship sending a signal back to Earth when Felix dies. We want to know how long after Felix dies does that signal reach Earth? So we know the speeds and everything and how we're acting here, right? And it's going to move at the speed of light, but we don't know that time. So if we manipulate our equation here, we can get the time to send back using that distance we just solved for, right? And it's going back divided by the speed of light will give us that time. And the next step here is we just convert that time that's produced in seconds. And we, again, use that Gen Chem unit conversion business, and we'll get 12 years. So that's that 12 years, though, is not enough, right? You need to add it to the 15 years being that delta t that we solve for up here, right? So basically, this is how long while we're in the spaceship, like as viewed on by the observer on Earth after for the cat to die, right? They have the time dilation. So that's that 15 years. And then plus the 12, which is going to take for the signal to come back. Oh, sorry, maybe that's a little confusing, but again, remember it takes 15 years for Felix to die as viewed on Earth, and then for the signal to be sent back to like at the time of death to be sent back will take 12 years. So in sum, the whole exchange is going to take 27 years. So that's why you can't just leave it as 12.